Alright, hello everyone. So in this video we're going to take a look at what we call trigonometric substitution. Well, actually, sorry, we're going to look at trig powers. So in other words, we're going to integrate functions that are powers of trig functions. Alright, so for example, let's consider. Right, I want to look at an example again, and then we'll talk about strategy. Right, so let's say I have the integral of sine cubed of x. Now, in this section, basically what we're going to be looking at is U-substitution. The way we're going to handle almost all of these integrals is we're going to approach the integral as a U-substitution. So if you think for a second, if I were to do U-substitution here, right, let me incorrectly show some work, right? So if I let u equal sine x, then my derivative of sine is cosine of x. And the issue with this is when I integrate, I'm going to have u cubed, and then my dx term is du over cosine. That's my dx term. So I end up with du over cosine x. So what ends up happening is I can't get rid of this x expression. Right, so I have u cubed du, right? I've changed my variable to u, but I can't get rid of this x expression. So what we're going to do in this scenario then is we are going to need to manipulate this original integral here, and we need to put a cosine into that integral, into that integrand. So what we're going to do in this case is we're going to break off a term. Right? So when we talk about the strategy a little bit more detailed in just a moment, what we're going to do here is we're going to write sine cubed of sine squared of x times sine of x. Right? So we're going to break off a sine term. Now, actually, what we're going to do in this scenario is we're not going to let u equal sine. What we're going to do is use the Pythagorean Identity, and we're going to write sine squared as 1 minus cosine squared. So what I'm in essence accomplishing here is now I'm going to let u equal the cosine term. So I'm going to have 1 minus u squared, and the derivative of the cosine is the sine that we have saved. Right? So for example, I'm going to let u be cosine. Oh, sorry about that. Let u be cosine. So the derivative is negative sine of x dx. Right? So yeah, in other words, one way that we can think about this is I'll solve for the dx here. Right? So I got du over negative sine of x, and that's my dx term. So now when I plug everything into my integral, we'll see the cancellation occur. Right? So we're going to have the integral of 1 minus u squared, and then I'm going to have the sine x, and the dx that we have over here is du over negative sine. All right, so again, we can see the signs cancel. Right? So I'm going to have the sine terms cancel, and then I have a negative 1 that I can pull outside my integral. Right? That's the way that I like to deal with it. Right? So I'm going to pull the negative 1 outside my integral, and I'm going to have 1 minus u squared du. Right? And what I could do algebraically, I could push the negative 1 back in and distribute, so I could have negative 1 plus u squared. I could definitely handle it that way. Personally, I like to take constants outside. Right? So again, I'm going to integrate each term here. The integral of 1 is u, and then the integral of u squared is 1/3 u cubed. And I have, the negative in front. Then I'm going to follow along. And then we had let u equal cosine. Right back up here, we let u equal cosine. So I'm going to plug back in my cosine. I guess go ahead and distribute the negative now. So I have negative, and then u was cosine, and this will become positive 1/3 cosine cubed, and then I have my constant of integration. So this is a general idea of what we'll be doing the entire section. So for powers of trig functions, we typically are going to do a U-substitution. So this involves a little bit of strategy. Right? And here's basically what our strategy is going to entail. It's going to say that if the sine function has an odd exponent, then we're going to pull a sine factor off. In fact, let's go back up to our example. Right? So we had a sine to an odd exponent. So the strategy is going to say take one of those sine factors, pull it off. And this we're going to save for the du piece. Right? So the du needs to be a sine, right? So what do I take the derivative of to get sine? Take the derivative of cosine. So the remaining part of the integral I need to get in terms of cosine so that I could let u equal cosine, just like we saw here. And then the derivative is the sine, and there's my du term basically waiting for me there. So our strategy that we're going to write down here in just a second is going to say if sine is odd, break off a sine term. If cosine is odd, break off a cosine term. So let's write a strategy here for a second. So what you look at in most textbooks, right, it'll say, let's say I have, I have sine to an exponent, and I have cosine to an exponent. This is what we're integrating. So we'll basically say something like this, right? If m is odd and n is even, then I'm going to say it this way, right? We break off a sine factor. So in other words, we would have the integral of sine of m minus 1, right? Because we broke off a sine factor, and we have our sine factor there. So we're going to let u equal cosine of x. Now again, remember to accomplish this, right? We're going to use the identity. And what do we have? Sine squared is 1 minus cosine squared, right? That's the identity that we would use in that case. And then the other scenario would be if cosine has an odd exponent. So what you'll typically see again in a textbook here, something along the lines of if n is odd, right, and m even, right, we're going to break off a cosine factor. We break off a cosine factor. Okay, so again, you know, that might look something like this. We're going to have the integral of sine to the m power. Now we've broken off a cosine factor, and we're going to save that for the du term. Right, so we're going to let, in that case, we're going to let u equal sine of x. And then we're going to use the identity as necessary that, you know, cosine squared is 1 minus sine squared. And again, I want to, you know, let me colorize this for a moment. So what we're doing here, right, this is going to be our du term, right? That's why we're letting u equal sine. And then in our first strategy, right, what we're going to do here is, I wrote that all weird here. All right, let me fix that for a second. Right, normally we write the dx last. Right, so I had sine of x that I broke off. Right, and again, I'm going to let this be the du term, because we have let u equal cosine. All right, so that's our basic strategy. So we're really doing, the only thing we're doing that's new here is the strategy. We're doing U-substitution. That's our technique of integration. We're not really doing anything new in terms of the technique. It's the strategy that would be new in this scenario. So, you know, let's look at a slightly different example. So let's say we have, as a different example, we have the integral of, let's say we have sine squared of x cosine to the 5th. Right? So following the strategy that we just wrote down, we have cosine that's an odd exponent. So we're going to break off one of the cosine factors, and we're going to save that for our du. Right? Again, yeah, let me highlight here. We're saving for the du. Okay? So what we're going to do in that case is we're going to let u equal sine. Right, and again, if we come back to our integral, we can see we already have a sign here. So this is going to be u squared. But the cosine to the fourth is not in terms of sine. So we're going to use the Pythagorean identity where we're going to write that in terms of sine. Now remember, our Pythagorean identity is that cosine squared equals 1 minus sine squared. So what we really have to do first, right, we want that to be cosine squared. Right? So I'm going to write that as cosine squared squared. And then I can use my Pythagorean identity there. Right, so in this case, we now have sine squared of x, and now we have 1 minus sine squared in our parenthesis that's going to get squared. And we still have the cosine x dx term that we have saved for our du piece. And again, let me come back up here in green. I apologize, a little bad board management here, right? So we have u was the sine, right? So our du is going to be cosine x dx, right? So we can see right here, this is my du term. This is du. Du is cosine x dx. Right? So I'm going to write this then as, I got the integral of u squared. I have 1 minus u squared squared, and then I have my du term right there. So we've accomplished getting the integral to u sub form, which we can integrate. We can solve this. Now, obviously, I need to do a little bit of algebra here. I need to, FOIL out this term, if you will, square it out, and then I can write this all as one big polynomial, if you will. Right, so, when I'm going to FOIL this, remember when I square a binomial, I square the first. I multiply these two and double. So negative u squared times 1 is negative u squared, and then I double that. And then I square the last. So my little, shortcut to FOILing a binomial, square the first, square the last, multiply these two and double. And then let me go ahead and distribute. So I'm going to have the integral of u squared minus 2u to the fourth plus u to the sixth. So now we can think of this as a polynomial form, and then we can take the antiderivative of each term individually. Right? So integral of u squared is 1/3 u cubed. This will be minus 2/5 u to the fifth, and then plus 1/7 u to the seventh. And then we had let u equal sine in this case. Right? Let me double check that that's what we did. Right? Yes, we let u equal sine up here. Right? So just want to make sure I'm plugging back in the right term. Okay. So I have u equal sine. So I have 1/3 sine cubed of x minus 2/5 sine to the fifth of x plus 1/7 sine to the seventh of x plus c. Right? So there is our final answer. Now remember, in the prior video we talked about two ways to check our work. Right? This is the antiderivative of our original integral. And what we can do is we can take the derivative of this and come back to our original integral. I want to point out to you that's going to be a little tricky. Right? So if I take the derivative of our answer, I should get back to here, but the problem is I have the cosine term in my original integral. So if I were to take the derivative of my antiderivative, notice how I don't have cosines in this formula. So it's going to be a little difficult to check this when I am taking a derivative. So I'm going to use my technology, and I'm going to check a little more efficiently. Right? So let me pull up my calculator. We talked about this in the video for 7.1. Right? So what I'm going to do is in y1, let's say I'm going to type in my antiderivative. Right? So I have 1/3 sine cubed. So keep in mind, when I'm doing a trig function to a power, I have to parenthesize the function. So I'm going to do sine of x, and then I have to raise that to the third power. And then what did I have? Minus 2/5 sine to the fifth. Right? So I'm going to do minus 2/5. And then parentheses, I have sine of x raised to the fifth. And then what was my last one? I had 1/7 sine to the seventh plus. Got plus 1/7. Close the fraction, and then I have sine to the 7th. Okay, so here's my antiderivative, right? And then I'm going to have the calculator create its version of the antiderivative. So ny2, I'm going to do math number 9. There's my function integrator. And remember what we talked about on 7.2 is we're going to integrate from 0 to x. Right? We want the antiderivative to be in terms of x, so we make our upper limit x. So remind me what we had. We had sine squared cosine to the 5th. So again, I got to put parentheses. I have sine of x, and then that has to get squared. And then I have cosine to the 5th. So let me put parentheses again, cosine all raised to the 5th power. So what's in y2, oops, I got to put my x variable, right? So what's in y2 should be the calculator's antiderivative, and what's in y1 is my version of the antiderivative. So I'm going to just go ahead and go to the table. Let me do second graph. I'm going to go to the table. It's going to take a second here for the calculator to fill this out. Right? This is a little bit intricate of an integral for it to evaluate, but I can see numerically that these match, right? So my antiderivative in y1 matches identically to the antiderivative in y2, so we know we have the same antiderivative. All right, so I want to talk about a couple other scenarios that we might see in this section. All right, so let's suppose that we don't have an odd powered trig function, right? So for example, let's suppose we have sine squared, right? So let's say the integral looking at is sine squared of x dx. So the strategies that we just wrote on the board a couple minutes ago discussed having sine to an odd power or cosine to an odd power, and we don't have that in this scenario. So here's what the strategy is in this scenario. Strategy is we're going to use what we call the double angle identity. So just as a reminder, right, if we have function to an even power, so basically sine squared and cosine squared. Now granted, sine squared is 1 minus cosine squared. But if we replace sine squared with 1 minus cosine squared, we still have a trig function to an odd exponent. Right? To an even exponent. If we replace sine squared with 1 minus cosine squared, we still have cosine to an even power. We don't have an odd power to use one of the strategies we just talked about. And if we had the integral of cosine squared here, if this was the integral of cosine squared, we could use 1 minus sine squared. But again, we're in the same issue where we don't have a trig function to an odd exponent. So we're going to use the double angle identities, which say sine squared of x. So we may use sine squared of x being 1/2 minus 1/2, cosine of 2x. Right? Or we have cosine squared, which is the same thing, but just a plus sign here. Yeah, and you know what? My terminology was incorrect. We call these half angle identities technically because we're converting 2x into half of that angle. Converting a 2x into half of that angle. So if you were to Google search half angle identities, these are the identities that you would find. So let's talk about how that helps us in this particular example. So we have integral of sine squared. So we're going to use the half angle identity for sine squared, and we're going to write this as 1/2 minus 1/2 cosine of 2x. All right, and I don't know if you notice right away the advantage here, but notice what we've done is we've reduced the exponent of a 2 down to an exponent of a 1, and I know how to integrate cosine, right? That's sine. So that's why in this scenario we will use the half angle identity. It actually reduces the power of the even exponent trig function. So I'm going to go ahead and split this up notationally, right? So I'm going to write this as 1/2, and then the dx distributes here. And then I'm going to say minus 1/2, the integral of cosine of 2x. Right, so I'm going to integrate each of these terms. Now, obviously, the integral of 1, right? The integral of 1 is x. So I have 1/2 x, right? And then the integral of cosine of 2x is going to be 1/2 sine of 2x. All right, now you might be asking, where's the 1/2 going to come from? Well, keep in mind, if I did a U-substitution for this integral, I would get a 1/2 out of that integral, right? I'm going to do it for this one example here, just to point out to you, right? If I was integrating cosine of 2x, technically, back in a Calc 1 class, you're going to let u equal 2x. Your du is going to be 2dx, so you're going to have a half du as your dx term. Right? So that's where this half comes from. So technically, right, doing a u sub here, I'm going to have cosine of u, and then I'm going to have half du. So the half comes out, and then the integral of cosine is sine of u, but that was our 2x. Right, now, in this section, I do not want to have to do, u sub for cosine of ax or sine of ax. So I want that to be kind of quick, efficient, quote-unquote, common knowledge. So when I'm integrating cosine of 2x, I just want to know that's 1/2 sine of 2x, and I don't want to have to go through this work. Right? Just want to point that out to you, and we'll generalize that in a second. So here's our final answer, right? Our final answer is 1/2 x minus 1/4 sine of 2x. Right? And that would be our final answer there, right? So we have 1/2 x minus 1/4 sine of 2x. Right? And again, I could check this answer on my technology. I'm going to take the time to do that, but I could if I wanted to. Right? So let me just point out to you here kind of strategy number 3. Right? So in our 3 strategies that we were talking about, right? Let me scroll back up for a second. We had said something like this. Right? Where did I write that? We had said something like, if we look at these functions, cosine to a power, sine to a power, right? If we're integrating sine to a power times cosine to a power, right? If sine has an exponent, we break off a sine term like we had here. If cosine has an odd exponent, then we break off a cosine term, right? And we're saving that for the du right here, right? But then the scenario we just looked at was, well, what if neither of them has an odd exponent, right? So the third strategy, if you will, strategy number 3, for the integral of sine to a power, cosine to a power, right? If both are even, if m and n are even, I can't even spell here, right? M and n are even. My e's, I used that e twice. That's what I did. If m and n are even, then we're going to use the half angle, like we talked about. Sine squared of x will be 1/2 minus 1/2 cosine 2x, right? And then cosine squared of x equals 1/2 plus 1/2 2x. All right, and then let's make a little note for ourselves, right, that when we do these problems, we are going to encounter something like the integral of cosine of a coefficient times x, right? And keep in mind that's going to be 1 over a sine of ax, right? So I don't want to have to, integrate a u sub there. And honestly, even though we won't see this in these problems, same thing applies for sine, right? If I'm integrating sine of ax, I'm going to get 1 over a cosine of ax, right? Technically, derivative of cosine is negative sine, so the integral of sine is negative cosine, right? So, but I don't want to have to do u sub on those problems. So these are the 3 main strategies that we're going to see for sines and cosines. So I want to look at a couple more examples for you here. One would be tangents and secants. So let's look at one other example here, and let's say we're going to look at a problem that has integrals of tangents and secants. So let's in this case say we look at tangent squared and secant squared. Is that what I want to do? Let's look at tangent squared and secant squared. Actually, let's do this. Let's look at tangent cubed of x, secant squared of x. Right. So the couple of the homework problems are going to have products of tangents and secant. So one of the strategies is if that secant is even, we're going to break off a factor of secant squared. Actually, you know, let me make this a little more exciting. Right. Let's get rid of that square. Let's make it a fourth power. So one of the strategies here is that if secant is even, we're going to break off a secant squared term. And we're going to save this for our du, right? We're going to save for the du term. Now, if you think about this for a second, you know, if that's my du term, what am I letting u equal? What do I take the derivative of to get secant squared? And that is tangent, right? Derivative of tangent is secant squared. So I'm going to let u be tangent in that case. Right? So following that strategy, then we're going to have the integral of u cubed. And then the secant squared, I have to get in terms of tangents. Right, so we have the Pythagorean identity that is similar to sine squared plus cosine squared, but it's in terms of secants and tangents. And that secant squared is 1 plus tangent squared. Oops, I still have. Apologize. And this is bad of me because I'm mixing variables. I'm mixing u's and x's together. So bear with me for a second. Right? I'm kind of midway through my substitution. Right? So this guy right here is my du term. Right? Think about it. If u is equal to tangent, then du is secant squared. Right? The du is secant squared of x dx. Right? Bad board management here. I should be fired. Right? So if I've let u equal tangent, the du is the secant squared. So this is my du term. And then I have u cubed, and I have 1 plus u squared du. Right? So there's my integral now, all in terms of my u variable. Right? So for products of tangents and secants, one of the strategies is if we have a secant to an even power, then we're going to break off a secant squared. Then the remaining secants in the integral we have to write in terms of tangents. And we know the Pythagorean version of secant squared is that it's 1 plus tangent squared. And then now, just like in our prior examples, right, we're going to go ahead and distribute, and we're going to integrate that polynomial expression. So we end up with 1/4 u to the 4th plus 1/6 u to the 6th plus c, and then our u was tangent. So we'll go ahead and plug in the tangent expression. Computer is just doing whatever it wants. So we have 1/4 tan x to the 4th plus 1/6 tan x to the 6th. So this is the basic concept in this section. Right? We're going to basically be doing U-substitution, and every time we attack one of these integrals, we have a specific strategy. So if sine is an odd, we save a sine. We let u equal cosine. If cosine is an odd exponent, we break off a cosine. We let u equal sine. And then if sine and cosine have even exponents, we can't save a factor, so we use the half-angle identities. And then if we have products of secants and tangents, one possible strategy would be if secant is an even power, then we break off and save a secant squared. All right, so a couple more examples. Actually, I'm going to do 2 more examples for you. So back in a Calc 1 class, you may have seen the integral of tangent of x. Right? So let me scroll back up here. Right, back in a Calc 1 course, you may have seen the integral of tangent of x. Now, what you would have done in a Calc 1 course, you would have written this as sine of x over cosine of x. And you would have done a u-sub. So you would have let u equal cosine, and the derivative would be negative sine of x. So when we do this u sub, right, notice that I'm going to have 1 over u, and then I'm left with sine x dx, right? So my sine x times dx is negative du. So that's going to get replaced with negative du. So I have negative 1 over u du. And then this is ln of u. Right? So the integral of tangent turns out to be the ln of cosine. Excuse me, negative ln of cosine. So this is an integral you should have seen in a Calc 1 class, and it just involves a basic u sub. Now, some textbooks write this as the answer. Some textbooks will say the integral of inverse tangent, integral of regular tangent is negative the ln of cosine of x. Now, some textbooks will simplify this a little bit to a slightly prettier version. So remember, there's a property of logarithms that says anytime I have a coefficient of a logarithm, I can bring that inside as an exponent. So I could bring the -1 exponent inside, inside as an exponent. And then this is the reciprocal, right? This is 1 over cosine. So I could write this as ln of 1 over cosine. And remember, 1 over cosine is secant. So usually this is the antiderivative that you will see for integral of tangent. And the reason that I point this out to you is if you're doing integrals in this section and you encounter the integral of tangent, that is a known integral. So you don't want to have to do this integral with u sub, right? You want to recognize integral of tangent as being a known integral. That's ln of secant. So the next example I want to do for you is also similar. So the future sections of integration techniques that we're going to look at, we want that integral to be recognized. We want integral of tangent to be known to be ln of secant. There's one other integral we want to treat in the same way. So let's take a look at this last example here. So let's suppose we have the integral of secant of x. We want this to be a recognized integral as well. So just like we did u sub on that prior integral, how do we develop the formula for this? And actually this is really creative. What we're going to do is we're going to take secant x and I'm going to multiply it by the number 1. And the version of the number 1 that we're going to use here is secant of x plus tangent of x. Right? So I'm going to multiply my original integrand by the number 1, and in this case there's the version of the number 1. So the advantage to what we just did there, which I agree isn't necessarily obvious, let me distribute the secant into the numerator. So I'm going to have secant squared of x plus secant times tangent, and then we're going to divide by our secant of x plus tan of x. So the cool creativity of multiplying by the number 1 is I'm going to let u equal the entire denominator. I'm going to let u equal secant and u equal tangent. Notice the derivative of tangent is secant squared, and the derivative of secant is secant tangent. Right? So if I let u equal the entire denominator, we're going to end up with just 1 over u du. Right? So the derivative of secant is secant tangent, and the derivative of tangent is secant squared. Right? So this entire numerator is my du term. All of this guy right here is my du term. Here's my du term. So I end up with that creativity, 1 over u du. Now again, would you have thought to do that? Most likely not, right? But in deriving our formula here, this turns out to be a very creative approach. So our final answer then here is that we end up with the ln of u. My paper is taking a mind of its own. Apologize for that. So this is ln of u, and our u in this case was secant plus tangent. So the last part of this conversation here, you actually won't see in your homework, right? You're not going to be given the integral of tangent in your homework as a specific problem, and you're not going to be given integral of secant as a specific problem. However, you do want to recognize these as known integrals, right? So, I'm going to switch to red, right? So the known integral, that should be a WN, right? The known integrals that we should get out of this section. And so as we work on problems in this section, we don't want to have to actually do the antiderivative for tangent. We just want to know that that's ln of secant x. And then if we were to encounter the integral of secant, again, we want that to be a recognized ln of secant x plus tangent x. Right. So all the other integrals in this section are going to involve you using the strategies that we discussed. Right. So these are basically problems that involve U-sub, and given a specific integral, you need to convert into a form where you can do the U-sub. So that involved saving the term, as we mentioned. If we encounter either of these last two integrals here, we're going to want to make sure those are recognizable. And we already wrote these down as well, right? But if I have the integral of, let's say cosine of ax, I want to recognize that as being 1 over a sine of ax. Right? I don't want to actually have to evaluate that with a U-sub. And then if I encounter sine of ax, I want that to be negative 1 over a cosine of ax. All right, this should arm you to be prepared to do problems of trig functions to exponents.